Hi and welcome to John's Maths Book. In this video, we're going to be looking at part 2 in the series of integrating using partial fractions. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. In part 2 of integration by partial fractions, we're going to look at a more complex problem with a polynomial of order 2 in the numerator and one of 3 in the denominator. The algebraic fraction here is difficult to integrate, so we must break it into smaller expressions in order to integrate. This technique is known as partial fraction decomposition. We can use partial fraction decomposition if the degree of the numerator is strictly less than the degree of the denominator. To better explain this, let's look at an example. We're going to try and find the indefinite integral of the expression shown on the board. Note that the polynomial in the numerator has a degree of 2 and the polynomial in the denominator has a degree of 3. And so this is suitable for partial fraction decomposition. Let's begin by factorizing the denominator. So leaving the numerator as it is, we have a denominator of x multiplied by 2x minus 1, which is again multiplied by x plus 2. Now let's look at the whole expression and get it into the form of a divided by x plus b divided by 2x minus 1 plus c divided by x plus 2. In order to do this, we need to work out what a, b, and c are. Treating this expression as 3 separate fractions that we want to add, we can now place them over a common denominator. If we now expand the numerator, we get the following expression. The next stage is to group the x squared, x, and constant terms together in the numerator. If we do this, we see that the x squared and x term have coefficients comprising of a, b, and c, and the constant term is minus 2a. The denominator remains unchanged. I've now removed the coefficients and constant from the numerator of this new expression and compared them with the original expression. As both expressions have only an x squared, x, and constant term in the numerator, and the denominator reaches the same, we can equate the coefficient of each and solve for a, b, and c. We could use Cramer's rule or Gaussian elimination to solve this set of equations. If you don't know how, please review my videos on these topics. In this case, however, it's more straightforward, as equation 3 has only one of the variables, so we can solve for a. So solving for a equals 1/2. If we now substitute for a equals 1/2 in equation 1 and 2, equation 1 becomes b plus 2c equals 0, and equation 2 becomes 2b minus c equals 1/2. Now multiplying equation 2 by 2 and then adding the equations, we can eliminate c. This leaves 5b plus 0 equals 1 and allows us to solve for b, which in this case is 1/5. Now, substituting 1/5 for b in equation 1 allows us to solve for c. So we have 1/5 plus 2c is equal to 0, and therefore c is equal to minus 1/10. So now we have a is equal to 1/2, b is equal to 1/5, and c is equal to minus 1/10. So now we've solved for a, b, and c. We can now substitute these values back into the original expression. This now transforms our original integral into 3 integrals, which are much more easily managed. So we're left with 1/2 multiplied by the integral of 1 over x dx, 1/5 multiplied by the integral of 1 over 2x minus 1 dx, and minus 1/10 multiplied by 1 over x plus 2 dx. Integrating these one by one, we can start with 1/2 times the integral of 1 over x dx. The integral of 1 over x dx is log of the absolute value of x plus the constant of integration. So we end up with 1/2 times the log of the absolute value of x plus the constant of integration. For the second integral, 1/5 times 1 over 2x minus 1 dx, we need to use u substitution. So if we start by letting u is equal to 2x minus 1, and then the derivative of u with respect to x is 2, so dx is equal to 1/2 du. Substituting these values in for x, we get 1/10 times the integral of 1 divided by u du, which equals 1/10 times the log of the absolute value of u plus the constant of integration. If we now substitute back in for u, we're left with 1/10 multiplied by the log, the absolute value of 2x minus 1 plus a constant of integration. And for the last integral, we need to evaluate minus 1/10 times the integral of 1 over x plus 2 dx. So again, using u substitution, we let u equal x plus 2. du by dx, the derivative of u with respect to x, is equal to 1, and therefore du is equal to dx. If we now substitute our value of u in for x, we have minus 1/10 times the integral of 1 over u du. So evaluating the integral, we have minus 1/10 times the log of the absolute value of u plus a constant of integration. And now if we substitute back in for u, where u is equal to x plus 2, we're left with minus 1/10 times the log of the absolute value of x plus 2 plus a constant of integration. So our final solution is 1/2 times the log of the absolute value of x plus 1/10 times the log of the absolute value of 2x minus 1 minus 1/10 times the log of the absolute value of x plus 2 plus a constant of integration.